morning, happy Monday. I hope everyone had a great weekend. Please bear with me today. I appear to have a little bit of a cough, but welcome back to the RedMars Podcast. As usual, I'm Astro Jake, your guide through the universe of space technology. Today we're driving into one of the most critical and fascinating topics in space exploration. That is communications. How do we talk to satellites, rovers on Mars, and even spacecraft billions of kilometers away? Let's break it all down. So let's start with why communication is vital. So space exploration isn't just about rockets and rovers. It's also about staying in touch. Communication is the nervous system of space exploration. Without it, we couldn't receive data from telescopes, control rovers, or monitor astronaut safety aboard the ISS. Today we'll explore how the magic happens, diving into the technology, the programming, and the science that makes all of this possible. So let's start with how satellites and spacecraft even communicate. Let's start with the basics. Communication in space happens via radio waves, a form of electromagnetic radiation. A satellite or spacecraft uses an antenna to send and receive signals. These signals are modulated, encoded, transmitted, received, and finally decoded back into usable data. So let's understand the first part of this, modulation. So let's look at some modulation techniques used in space communication. We'll dive into how data is encoded onto radio waves for transmission. This is the realm of modulation techniques. Imagine the radio wave as a blank canvas, and modulation is the way we paint. We paint this data onto that canvas. Let's explore the most common techniques used in space communications. First one we're going to look at is phase shift keying. PSK, or Papa Sierra Kilo. PSK is like a secret handshake between two friends. It involves changing the phase of a radio wave to encode data. So how it works, the phase of the wave shifts between predetermined states to represent binary data. For example, in binary phase shift keying, BPSK, the wave can either have a 0-degree phase shift for a 0, or a 180-degree phase shift for a 1. More advanced forms like quadrature phase shifting keying, QPSK, use 4-phase states. Example, 0, 90 degrees, 180 degrees, and 270 degrees, allowing it to encode 2 bits per symbol. So when we say phase, I realize maybe not everybody knows exactly what I'm talking about. So if you take a piece of paper and draw a waveform, so think of it like an ocean wave. It goes up, it goes down, it goes up, it goes down. Where you start drawing that waveform from is, say, 0. Now, that first up and down could be the first part you're going to modulate. So to phase shift that, instead of having the wave start at 0, you can move that. So say it starts at -1. So then you're in the peak of the wave at 0. Say that's 90 degrees. You've just shifted a wave 90 degrees. We won't go too much more into that, but that's just kind of the visual I wanted to give there. So let's look at BPSK. So the BPSK waveform looks like a smooth sine wave that flips direction abruptly at each data transition. In QPSK, the wave shifts to one of 4 phase angles, resulting in a more complex pattern. So, usage in space. PSK is popular in satellite communication for its robustness against noise, essential for long-distance signals. So next, let's look at frequency shift keying, FSK. FSK is like playing musical notes to send messages. It uses changes in the frequency of the wave to encode data. How it works. A radio wave alternates between 2 or more frequencies to represent binary data. For instance, a higher frequency might represent a 1, while a lower frequency represents a 0. A more advanced form, multi-frequency shift keying, MFSK, uses multiple frequencies, allowing for more bits to be sent per symbol. So how do we use this in space? Well, FSK is used for low bandwidth applications, such as telemetry data, where simplicity and reliability are key. Quadrature amplitude modulation, QAM. QAM is the multitasker of modulation, combining both amplitude and phase changes to encode data. So how this one works. In QAM, the amplitude, in quotes, strength, a phase of the wave are varied simultaneously. This creates a grid of symbols on a constellation diagram, where each point represents a unique combination of amplitude and phase. For example, 16 QAM has 16 points, 4 bits per symbol, while 64 QAM has 64 points, 6 bits per symbol. So, the waveform is a blend of amplitude and phase changes, resulting in a pattern that is harder to visually interpret compared to PSK or FSK. But how is this used in space? So, modern systems increasingly use QAM for its efficiency, as it can transmit large amounts of data over limited bandwidth. However, it requires a stronger, cleaner signal, which can be challenging for deep space missions. Protocols and programming in space communication. Once the data is modulated, it needs to follow strict rules and protocols for transmission. So, let's look at some of these protocols. The Consultative Committee for Space Data Systems, CCSDS. This international standard ensures that space agencies like NASA, the European Space Agency, ESA, and others can work together seamlessly. CCSDS governs how data is formatted, transmitted, and verified. Protocols often include features for error correction, such as Reed-Solomon coding and convolutional coding to ensure data integrity despite interference. So let's look at some of the programming languages we might use for such communications. So C and C++. These languages definitely dominate the space communication system development due to their speed and ability to interact directly with hardware. Now, Python, on the other hand, is mostly used for testing, data visualization, and simulation of communication protocols. It's especially popular among ground control teams for its simplicity and versatility. So, Python, I'm sure a lot of people getting new into like the programming world and that will look and compare. A lot of the times it's C++ or Python. Which one do I want to start with? Well, C++ looks pretty complex. I'm going to go and start with Python. Well, Python's definitely a great place to get started for programming, especially if you're looking at, some of these communication techniques. So you can do that and simulate some of these communication protocols, and it really helps to learn and run through, say, some of the modulation techniques. Now, in practice, you'll more than likely be using C or C++. With that, I would say if you're looking to turn this into a hobby or actually make some use out of these things, maybe program a microcontroller or some software-defined radio, I would suggest looking at C and C++ to begin and really taking the time to understand. There are some great tutorials out there, and it's actually a lot of fun. I do a lot of C and C++ in my own role in the job that I do, and I've never regretted it. We do use Python, but mostly, again, for the simulation side of the world or some quick testing. Now let's continue on. So, modulation techniques in action. Imagine sending an image from a rover on Mars to Earth. Here's how the process might look. The image data is compressed and encoded using a protocol like CCSDS. It's modulated onto a radio wave using, say, QPSK or 16 QAM for efficient transmission. The Deep Space Network, DSN, receives the signal, demodulates it, and decodes the data, ensuring error correction along the way. Finally, ground control receives the pristine image of the Martian landscape. So, modulation, decoding, encoding, all of this are good techniques and techniques that are used in practice to make sure your data is getting from A to B. And a lot of these, like I mentioned, ensure error correction. So we'll look a little bit at that. So what is the redundancy and error handling in these systems? Space is unforgiving. Signal interference, noise, and sheer distances involved mean we need robust error detection and correction. Algorithms like Hamming codes, Reed-Solomon codes, and convolutional codes are staples in space communications. They allow the receiver to detect and even correct errors in transmitted data. For example, the Voyager spacecraft relies on Reed-Solomon coding to ensure data integrity despite signals being billions of kilometers away. Redundancy. Satellites often have redundant communication systems, such as multiple transponders or antennas, to ensure continued operation in case of failure. On the software side, algorithms constantly monitor signal strength and switch to backup systems if anomalies are detected. Now, we'll have another episode where we talk a bit more about redundant systems in relation to the space environment, as we previously touched on in other episodes. but there's a lot more we can go in depth there, so we'll save that for another episode entirely. So, networks in space, past, present, and future. So, communication networks have come a long way. Let's start with the Apollo missions. The Apollo missions relied on a network of ground stations worldwide. Signals were transmitted via S-band radio frequencies to track the spacecraft and send telemetry data. Voyager missions still communicate via NASA's Deep Space Network, DSN. The DSN uses large parabolic antennas across the globe to maintain contact with spacecraft up to 23 billion kilometers away. Our present day, TDRS, Tracking and Data Relay Satellites, a constellation of satellites in geostationary orbit that ensures near continuous communication with the International Space Station and low Earth orbit satellites. Now we have Starlink and something called OneWeb. These commercial satellite constellations aim to provide global internet coverage using inter-satellite laser links to relay data efficiently. Now there are other ones coming down the line, including those from Amazon, but they're not quite there yet. Alright, what do we have in the future? Lunar and Martian networks. I cannot wait. So NASA is working on creating a lunar gateway communication hub to facilitate a permanent presence around the moon. That's something to think about. Now, just taking a step back here, looking at lunar and Martian networks and that, and we previously spoke about GPS, so the Global Positioning System. Many people might not understand that GPS actually only works here on Earth. They are around geostationary orbits of the Earth. So in order to establish that elsewhere, say like the moon or Mars, we're going to have to build a network of satellites around those planets as well, or those moons, in order to allow us to have some sort of positioning system there. Those do not currently exist today, but I ensure they are definitely being looked at. Alright, so what do we have next? Quantum communications. Research into quantum entanglement could revolutionize space communications, offering secure, instantaneous data transmission no matter what the distance. So, just to give a very quick, example of what quantum entanglement is, think of you have a coin in your hand, and then your friend somewhere else on Earth is holding another coin. And I were to flip that coin from heads to tails, and now their coin, where they are, would also go from heads to tails at the exact same time I flipped mine. The only way that is possible is if those two coins are quantum entangled, meaning they represent the same state across space and time. There's no delay, no nothing, because they are at a quantum level. So that's very cool that there are companies and research facilities looking into this, because once we get to that point, we go back to the basics. We only need to have ones and zeros, binary data. And if we can quantum entangle 2 bits, thinking 1 and 0, across, I don't know how many, then you can have a transmission of data really anywhere in the universe happen instantaneously and securely, at least to this point. We don't know how we would do a man in the middle or something on something like that. So, or if that's even possible. But just a cool technology and bit of science that's currently being researched that I am fascinated with and very interested to see where that goes and what comes from that. I have heard in the past that they were working on some quantum entangled phones. I don't remember the research agency that was working on this, but they did make some claims that I'm not sure if they were debunked or not. But very, very cool research nonetheless. So let's look at deep space communications. So, communicating with spacecraft millions or billions of kilometers away is no small feat. So, one of the first challenges you have is signal delay. It takes about 20 minutes for a signal to travel between Earth and Mars one way. Then you have power constraints. Spacecraft like Voyager operate on minimal power, so the signals are faint and require powerful Earth-based antennas just to detect them. Again, if we get to our quantum level, this no longer becomes an issue, at least for the signal delay. Now, power constraints is another thing. Quantum typically ends up using quite a lot of power, but if you have them entangled, I guess you could do it on a very low power since it's at the atomic level. Anyways, we'll continue on. We won't get sidetracked here. So, what are some of the solutions to this? So you have high gain antennas, like we just mentioned. They use narrow, focused beams that allow data to travel vast distances. Then there's the Ka band communications. Modern missions are moving to higher frequency bands like Ka band, which offer more bandwidth for data. Then there's data compression. Advanced algorithms compress data before transmission, ensuring that every bit counts. That's a joke. Anyways, international collaboration and competition. So space communication is both a collaborative and competitive field. So from the collaboration side, the International Space Station, or ISS, relies on contributions from multiple countries, including NASA, Europe, the European Space Agency, not really a country, but agencies, the Roscosmos, and JAXA. They all maintain communication networks. There's joint missions like the James Webb Space Telescope that use globally shared communication systems. But there's also competition. So some countries develop independent satellite networks to reduce reliance on others. For example, China's Beidou navigation satellite system competes with the US GPS and Europe's Galileo. Now, we previously spoke a little bit about the programming languages for space communications, but we'll touch on it a little bit more in detail here. So, space communications rely heavily on software engineering. Hint, hint, great job if somebody's looking for something to do at the undergrad level. Lots of jobs out there. So, languages again, C, C++. This is a low-level programming language that is used for hardware communications typically, can be used for some higher level stuff, and there are even front-end libraries for these languages, so you're not just stuck with the low-level stuff. It's a bit more complex to learn, but well worth the time if you're willing to put the effort in. All right, Python, or MATLAB, is used for simulations and data analysis. I've done a lot of Python in my past. I've done some MATLAB. Python's more of kind of a scripting, where MATLAB, if you're unfamiliar, it's used in a sort of IDE or development environment, and from there you can do things like autocode, C and C++ code as well. But yeah, Python's a great language to get started with. MATLAB if you're more on the mathematical side or physics side, both great for simulation and data analysis. VHDL and Verilog, words you don't hear very often, or languages you don't hear a lot of very often. They're very, I'd say, niche and rare, especially in today's environment, to find individuals with that skill set. But this is used for designing communication hardware like FPGAs, and it's a very, very good language to know if you're doing anything with those types of FPGAs, and that's Field Programmable Gate Array. Not that you need to know that, but that's what that stands for. But yeah, we'll move on. So simulation tools. Engineers use tools like ANSYS, HFSS for antenna design, and Omnet++ for network simulation. Cool tools to look at. Feel free to Google and dive a bit more into those. We'll only just kind of mention them here. All right, so what does the future look like for space communication? So looking ahead, the future of space communication is filled with all kinds of promise. We did mention the switch over to the Ka band, but let's look a bit more at the quantum communication side. So leveraging quantum entanglement could eliminate delays and offer unhackable channels for secure communication. China's Micius, I'm not sure exactly how to say that, but MICIUS, their satellite has already demonstrated quantum key distribution in space. So again, huge breakthrough, and I hope more progress is made there, both in the US and allied countries as well. AI-driven networks. Using AI to dynamically allocate bandwidth and prioritize data could make networks more efficient. AI is changing the world we live in today, so if this can be applied to network allocation, I think there could be some promise there, for sure. Autonomous systems could manage deep space networks without human intervention. Removing some of the human error. I'm not sure if the AI tools are quite there just yet, but with some more development, I think we could get to a state that at least relieves a lot of that human intervention. All right, interplanetary internet. NASA and the ESA, that's the European Space Agency, are working on protocols like DTN, delay-tolerant networking, to create a reliable internet for missions to Mars and beyond. Very exciting. Lots coming down the line, and every day we hear about more breakthroughs, so it's super exciting. Well, communication is the invisible thread connecting humanity to the stars. It's not just about sending data, it's about making exploration possible. As we push farther into space, the technology and collaboration driving these systems will only grow more impressive. So that's all I really have for this episode without diving too much into detail on these topics. Again, we wanted to focus just on the basics. So thanks for joining me on today's journey. Don't forget to subscribe to the RedMars Podcast and for more adventures into space technology. Until next time, keep looking up, stay curious, everyone. Take care.